Alright, so yesterday we were talking about what we are going to do in this course mainly. देखो, while these things are important, आज की डेट में this architecture has become much more important. Okay? अच्छा एक चीज और, see, I said कि so let us talk about that again. I had said कि मिड टर्म 1 अपने होगा 15, मिड टर्म 2 20, एंड टर्म 35. दिस रिमेन्स, ये 70 तो मेरा कभी कहीं नहीं जा रहा है. ओके, नाउ आई हैड सेड प्रोजेक्ट 25, राइट? प्रोजेक्ट को मैं 20 कर रहा हूं. अटेंडेंस 5 एंड स्क्राइब नोट्स 5. ओके, सो हर कोई नहीं करना चाहता क्या? सी हाउ मेनी ऑफ यू आर विलिंग टू डू, हाउ मेनी ऑफ यू आर विलिंग टू स्क्राइब नोट्स? मतलब जो लेक्चर होगा उसके नोट्स बनाने पड़ेंगे, उनको लाटेक में लिखना पड़ेगा. आज जनरेटिव एआई की डेट में क्या लाटेक और क्या पाइथन, क्या बात कर रहे हैं? Think over it, think over it, else I mean I'll not make it compulsory for everyone, but I want कि कोई ना कोई फिर रहे, then उन लोगों के लिए I'll increase this percentage then. Okay, सोचना इस पे एंड मेरे को बताना. Right, so this is what we were talking about. Okay, देखो, in traditional computer science what we have been doing until now is you are given some input, you also know what output should be, and then you basically devise a method that given this input gives you that output, right? As simple as that. Whatever it is, be it sorting algorithms, whatever it is, you are always trying to devise an algorithm, basically a function that will take input and give you the desired output. Machine learning opens up a new paradigm, which is I will try to approximate this f. See, I cannot give you guaranteed f. There are no guarantees whatsoever that this is the best f you can find in this much time. No guarantees like that wherever you, those kind of guarantees that you used to have in algorithms and data analysis, right? Here the simple thing is I can give you an f, it will try to approximate what you are looking for. It may or may not be best, it may not even work. Okay, so but I will give you some f for sure. So whole machine learning, right, is dedicated to this. You want to design, you want to learn this function f. Now whether you do one course on machine learning, I think I have said this in reinforcement, I mean AI as well. Whether you do one course on machine learning or whether you do 50 courses on machine learning, what is their main goal of all these 50 courses? What will be the main goal? Generalization, right? You want to learn a function that generalizes well on unseen data, right? I don't really need any learning if I were to test my algorithm only on the training data, because for that I already have answers, right? So I won't really need to learn anything if I am just talking about the data set that is given to me in training. I want my this function f to generalize well. Okay, and if that does not generalize well, what do we call it? Overfitting. Okay. All right, so coming to this simple thing, this is the network we were talking about, and at least for some time I will be just talking about this one. What do we do next? Since you already know linear regression, so you have to help me out here. I don't know it much. So, yes, how do we proceed? How do we proceed? By this is what I have. See, okay, that's good. This reminds me एक बार थोड़ा सा. So देखो, you will generally encounter three kinds of graph in machine learning, right? So एक बार so first one is called, I mean there can be more names for this. What is a scatter plot? I mean, okay, so you may even drop this word if you want. The first plot is you are just plotting the data that is given to you. Okay. Now, for this drawing, I will drop even B. Okay. So, let us say this is my W. No, is this correct? No. What I have here is X and I have here Y, right, whatever it is. So, let us say it turns out to be this one. Next will be which graph? So, this is you are simply plotting data, no learning as of now in this first kind of graph. In second kind of graph, what you will have is, so I am dropping this B now, because what will happen if I include B dimension? So, you know, I will need 3 axes, one for W, one for B and one for something else, right, and I would not be able to draw that. So, that is the reason I am dropping B, and generalization nowhere goes. One variable is good enough to give us intuitions in even a million dimension vector space. W, what will I draw here? So, let me now take realistic examples that actually pertain to apne linear regression only. So, let us say your data looks something like this. Okay. Now, let us say this is how my data looks like. What am I supposed to find here? If I want to predict it for, let us say, some data here which is not there in my training data set, right, what am I looking for in case of linear regression? Yes. Everybody knows here. See, this is your training data. Let us say you have plotted all your training data. My question is, when we are doing linear regression, what are we looking for? What is it that we want to do? We want to find the best fit line. So, let us say this is my best fit line. Okay. Now, how do I find this best fit line? So, one more thing, what's wrong with this line? And similarly, so how many lines can I draw here? Infinite lines. What are the degree? I mean, I can have infinite intercepts and I can have infinite slope, right? So I can rotate in 360 degrees and I can have different intercepts. Does this give me the complete set of all the lines possible in this plane? Yes. Okay. Now you have this one, let's say. Tell me, how do I find the best line? Optimizing W and B. So you can even drop B right now. We'll come to it in the end and we'll say ki in B dimension same things happen. Yes. Most of these? Right. So that's a good point. Can I have a line that covers most of the points? Let's say my data looks something like this. So let's say my data looks something like this. Best fit line, will it pass through any of this? Right. So what am I supposed to do? I mean, if you do it through MSE, maybe somewhere here, right? So what is our goal here? Don't tell me what MSE does. उससे पहले. My question is this: what do we mean by bestness of a line? Who defines this bestness for you? That when we say I want the best line, right? What do we mean by this best? Say it again. My prediction is near to. So basically you are saying my prediction should be closer to the actual label. Is that what you are saying? Okay. Anyone else? Right. So the line that generalizes well. Now you see all these bestness, right? They are not best per se. Some of you might come here and say, see, in linear regression this will be the line, but for my this particular application which I don't know what will it be, but some of you can come and decide ki nahi yaar, line should actually be either this one or this one. I don't know. I will not be able to give you an example, but let's say this happens. Will MSE work? So the first thing that you have to keep in mind is your assumptions are very much important here. And what is the assumption in this case? I am looking for a line and I need to know what do I mean by best. Best ye nahi hai ki it is best, because we said in machine learning there is nothing like, you can't give bounds, you can't, so bestness you have to define first. What do you mean by best, right? So in this case, one thing is for sure, which is I cannot have a line. So tell me one thing, if all the points were collinear, collinear means on the same line, right? Do I have much to learn there? Probably not, right? Probably it's not even a machine learning problem, probably, okay? If all my points are collinear, I simply take the line that is passing through all the points and I am done. I don't have anything else to do. Problem lies in this kind of, and what is one problem that I am adding on my own in linear regression? I know there cannot exist a line that passes through all the points, right? This won't happen because these points are not collinear, so I will not have a line that passes through all this. Then comes the notion of best fit line. Now, how do you define this bestness? You already know this. So, how do you define this bestness? Through cost function. Okay. So, that is what we have here. and this line wx plus b, I am dropping b for the time being. Okay. So, what is it that I am actually dropping, intercept or the slope? I am dropping intercept. So, I am assuming every line passes through origin. Okay. But I mean probably this will not fit here, but can I still do this, fix b equal to 0 and find the best fit line? That can still be done. Okay. So, in that case best fit line will not look like this red one, but maybe something like this, because this is the best we could do, right. Alright, so what is this guy? What is this second plot? So, this second plot you will be plotting w with respect to j. Now, let us say you have a plot something like this, let us say you have it. Okay. So, we go to next one. I will call it second kind of plot and this is third one. What happens in this one? So, in third one what you have here is, you have epoch with j. What is j? J is my cost function. So, let us say something like this happens. What does it mean? In both these plots we have j on y axis, right, and what does this kind of plot mean? So, you can assume this is monotonically decreasing. So, somewhere here it looks like it's going up. It can behave that way too, but right now I do not want it to behave that way. Yes. So, what is that third one kind of thing? Number of epochs, cost function, these are the values you actually observe. You will not be able to see this in almost 100% of the cases. Why so? Why you will not be able to have this in almost 100% of the cases? Because you will not have just one dimension, right? You have some tens of dimensions, if not hundreds or thousands. So, if you have more than one dimension, this plot is already in 3D, right? You will have to rotate this figure in different ways to figure out how does this data look like. The moment it is in 3D, right? You have W1, W2 and B, then it's beyond our imagination, right? We will not be able to imagine this. So, even though you can plot this, it just does not make sense. We will not be able to visualize this. This plot is not going to help you, right, unless you start drawing just one variable. Next one, what is this guy? What's good or bad with this? Good with this is, this looks like a differentiable function, right? If a function is differentiable, will it be continuous too? Right? Okay. So, this looks like a differentiable function. So, fine. What about this guy? I mean, I am not talking too much about this because, so what is wrong with this? See, the first question that you have to ask, is this even a function? Is this a function? Or let us say if I, so maybe I will help you. Is this a function? This is certainly not a function because, right. So, any line that you draw parallel to y axis should intersect a point at most at one place, right. In this case, a line that is parallel to j intersects more than once at least at one place. Even if this happens at least at one place, that entity is not a function. So is this a function now? Yes. कहाँ पे मेरे को बताओ point वही. Give me a point where a line parallel to J will hit at 2 points. लग रहा है क्या कहीं पे, तो फिर मैं चेंज करूं. To me this is a function. कहाँ पे गड़बड़ लग रही थी बताओ. Okay. All right. Now, how did you define bestness? Bestness of a line? How did you define bestness of a line? Loss function as minimum value. I have problem here now. Loss function as minimum value, even though I don't understand this right now, but which minimum value? This function has so many minimas. And almost all optimization methods, I won't generalize it, but this is a pretty loose statement, but most of it is true. All optimization algorithms will suffer if they end up being in any of these local minima, right? And let's say this function extends like this to infinity on this side and to infinity on this side. That means I have infinite local minimas, I can get stuck anywhere. So I don't want this kind of a loss function. I want better loss functions. Stop here for a second. Last one. Will this help me much? Will this second kind of plot help me much? Why not?
Because it will not give a particular value after which we should stop. Like we feel that it is the best fit line if we need.
No, I'm not talking about best fit line, this one. I'm talking about this one.
I'm saying that it will not indicate at any point that we have to stop here or after this or obtain a optimal value.
No, if I can draw this, then I can tell you this is the minimum value and I'm done. बोलो बोलो. If I can draw this and visualize this, this will actually help me a lot. Problem is same as this one, right? Right now you have just one W, so you can draw this. Okay. Now the fact that I am able to draw this, does it guarantee that somewhere later it is not going below this one? No guarantees, right? Somewhere later it can actually start falling and go somewhere at a place lower than this one, right? But most likely this is one variable, so you will still be able to figure out those things. But that's a hard problem anyway, so the problem is not solved. It becomes manifold if you have multiple W's. You have W1, W2, W3, and then you are supposed to draw this with respect to J. This function becomes complicated again and it does not help me visualizing things anymore. So this particular plot, even though looks fancy, does not help me much. What about this last one? When you are in high dimensional space, this is what machine learning community does, right? This is the only plot that we can draw and we can deduce some conclusions. What is this? Number of epochs. That depends on me. Okay. This is cost function. If the value of cost function is decreasing on my training data, then I am doing it right. Okay. And what I will also expect is that the cost on that the cost on test data is also decreasing like it is. Okay. So, this one helps us. Linear regression, logistic regression are two simple algorithms where even 1, 2 and 3 all will help us. Okay. So, for linear regression we will be drawing all these 3, particularly 1 and 2. Okay. Alright, so we start now. So, this one, this is how since it is linear regression in one variable, I can draw this, and right now I am dropping B, I will bring B into picture later. Okay. So, all I have is y hat equal to Wx. Now, this is actual y, this is actual x. Where does my y hat lie in this particular figure? Yeah. Yes. Where does my y hat lie? Exactly, right? The line, it can be any of these lines that I am calling best fit line, right? That is my y hat. So, I mean not best fit line, any line that I can draw on this plane will be my y hat. I need to improve it. So, I need to get rid of this one. I do not really like this graph now. None of us likes because it gives us no guarantees. So, I am looking for a best fit line. How do I define this best fit line? How do I define this best fit line? You know this already. Have you done PCA? Yeah. No, but more than that, you know what does it, how does it work? Chalo, we will come to that later. Huh. So, what do I do in linear regression now? How do I find that best fit line? Mechanism batao mere ko. Cost function. So, I have to come up with a J. How will my J look like? So, ekdam, don't tell me what you have, you know, in your minds, in the sense that जो भी याद किया हुआ है, don't tell me that. Just come afresh. I want to define this cost function for my linear regression, where I am supposed to solve this problem that I want a best line that fits here. How do I do it? So, rightly said. So, one way to do this is, if this is the answer, so if y is the label, so now see, since I am directly talking about labels without talking about unsupervised, supervised, this is, we are already into supervised machine learning. So, y minus y hat. What is y? Actual label. What is y hat? My algorithm's prediction. Okay. Now, if for all the cases they are all the same, then I am on right path. At least it seems I am on right path. Okay. Now, this should happen for all examples. So, let us say this I in parenthesis in superscript implies which example we are talking about. So, this is my ith example, and this should happen for all examples. What should happen for all examples? I am looking for this difference. Okay. What do I do with this? So, it might happen that answer was 100, my prediction was 80. So in that case this difference is 20. But let us say it can also happen that this is 100, this is 120. In that case I will have minus 20. And if these are the only two examples I have, both these examples errors will cancel out, I will get a 0. Even though error is not 0, I am still getting 0. How do I solve this? Square. देखो ये पूरा जुगाड़ चल रहा है, right? How you deduce this is some kind of a mathematical जुगाड़. Now you squared this because you don't want negative errors to cancel out, you want each error to add up to the cost function. It does not matter in which direction you made the error, it is a error nonetheless. What happens next? Summation. Okay. Summation. So summation कुछ ज़्यादा ही दूर बना दिया. Summation. Summation over what? This variable here is for all my examples. So I go from I equal to 1 to m. Okay, m is my total number of, लिख लो, right? So write all these variables later. All right, is this enough? Is this enough? Why not? No, I am saying, is this enough? Is this cost function enough? Yes, yes. That is what we are looking for. Anyway, continue what you wanted to say. Is this sufficient?
Yeah, it should be, but for optimization they say that we should divide by 11.
How many of you go for this is sufficient? So this is sufficient, right? Like you already said, this is sufficient, there is nothing wrong with this. But the problem is, so let's talk. So there are 5 things involved in writing equation for MSE. One is this difference. Second, you can have this difference to be negative, so you square it. Then you sum it over all the examples and then you take the average. There is absolutely no need to take this average for whatsoever purposes except what I will mention. Okay? And now, what is the another thing? What is that 5th thing? 4 things have come: difference, square, summation, and then this 1 by m, so that you have average. And now you have this 2 sitting here. This is my j of w comma b. Right now b is not there, b is 0. So this is j of w right now, but in general I will write it like this. So right now b is 0, this is my j of w. Right. Is this fine? We have still not talked about about this 1 by m. Why do we need this 1 by m? Huh? For every attrition, see, without this 2m, this formula is fine, there is absolutely no problem with it. You need this 1 by m, you compute average, because let's say this side, let's say we have 3 data sets, 3 teams are working on it. They have 100 examples. You have 10,000 examples and these guys have 1 million examples. right, of the same kind. So 1 million, subset of those 10,000 is here, subset of those 10,000 is here. Now when you will draw cost function, how will the values look like for this side? Since they are working only on 100 numbers, so their j will be much smaller compared to this team, and their j will be much smaller compared to this team. Even though all of them are working on the same problem for same thing, they will have different uncomparable values of j. But you remember how sampling works? If I have sampled randomly, right, then most likely the average of all these guys will coincide, right? They will be comparable if not same, compared to just taking the absolute sum, right? So we prefer averages so that we can compare. Now we still have this 1/2 sitting there. Why? Right, because the method that we are going to deploy to do whatever later, right, that has differentiation. So we will need to use differentiation, right? So our optimization method will be derivative based. In that case, you have a square here, and you said I don't want to keep writing this 2 every time. So that's precisely the reason, right? So that I want to get rid of this 2 in the very next step, just multiply it by 1/2. The moment you have it, you will differentiate this, you will have 2 come there, 2 cross 2 cancels out in the very next step, and this is the reason why you have it there. Okay? Any questions about this? Any questions about this? Sure. Next. So I want to draw this here now, because this is my cost function for linear regression. How do I do that? Hmm? Right, y is equal to x square kind of thing. So what is my input here? How do I draw this guy? How do I draw this? मेरे को नहीं समझ में आ रहा. Can I draw this equation as it is written here? No. Silly change करना होगा, but what change will that be? Substitute y hat for wx. Okay. So this term becomes wxi. And now you have this as a function of w. Everything else, xi, y, m, everything else is a number. There is only one variable, that is w. And when you will open, so this whole thing now looks like a squared term, right? And square is a, what's the equation of a parabola? Y square equal to 4ax. Is that the most general equation for parabola that you can write? Y equal to 4ax is, you know, very smooth, that no, any parabola in this. Y equal to ax square plus bx plus c, right? This will capture every parabola that you can write. Now, does this have of that same kind? Yes. Okay. This is a squared function, looks something like this. So ये पूरा जुगाड़ करके MSE पे क्यों आए? Why not that kind of thing which I had drawn earlier? Because even though it was just one variable, it still had infinite local minimas. I don't know which one is the global minima. I want to go there. And by the time I'll finish this course, I'll tell you we don't really care about global minima. But in first class, we care about it. Okay? So mathematicians, they care about maybe global minima. As a machine learning engineer, we don't really care about global minima. What is that one thing we care about? We care about only one thing. Our algorithm should generalize well. If it is global minima that gives me this property, fine. If it is something else that gives me this property, I'll prefer that other place compared to global minima. Okay? So I have got this from this. So this was a nice coincidence that I could keep writing this, and this function turned out to be a convex function. This was just a coincidence, or you can think of it this way, that those who were designing it, they were thinking both ways. I should be able to write down a good closed equation, at the same time it has to be a convex function. If it is not convex, what problem do I run in? See, what is the good property of a convex function? It has only one minima, and which of course is global, local, everything. Okay? So, and it does not matter how many dimensions you run in. So, if instead of writing Wxi, if I write, W1 x1 plus W2 x2 plus W3 x3 all the way until Wn xn plus b, it does not matter. It will still be convex in that dimensional vector space. Right? So, it is not that it is convex only in this case, it will be convex in every dimensional vector space. Questions here? All right. So this is fine. We get this. I am still not understanding how do I relate these two pictures now. Yes, how do I relate these two pictures?
So we get W for which the cost is minimum, and then we can predict the point.
So what happens, for example, if my W is this? Yes. So, one more thing. I'll talk about it when we'll talk about gradient descent. I think the worst analogy of gradient descent is the one that is the most common. I don't like it, but it is everywhere, which is, think of you are on a hill somewhere, and then you want to come down to the bottom of that hill, right? So you are here, this is the W. This is the W, or maybe let us say somewhere here. Cost function is, so let us say here only. Let us say value of cost function is high. High compared to what? High compared to the minima, right? So maybe W was higher, so let us say maybe this was the W, or since we are passing it through origin, let us say this was the W. This was the line corresponding to this W. How do I make it better? See, here we can visualize everything. You won't be able to do it in higher dimensions. So, let us say this one, I can see maybe if I tilt it like this, it will be better. What do? I need to come to this side, but right now here I can see I can come to this side visually. I will need an algorithm that does all these adjustments automatically. So, let us say I come here. Finally, I want to come here, let me call this as W0 and let us say this is that line. Can I do anything better for this setup? I can't do anything better for this setup. So, the line corresponding to W0 is best in this sense. Okay. So, you have the best line if it corresponds to W where your J is minimized. Questions? We have done everything graphically right now, right? In the next class, we will introduce an algorithm that does this for us, and the name of the algorithm is gradient descent. Okay? Chalo, done for today.